Alright, so there are a lot of additional functions in MATLAB that are extremely useful, especially from a data analysis standpoint. The function that I can give you examples of are things like the max function, which will return the maximum value of an array or a vector in a row in that matrix. Like I said, it's very useful to find out what the maximum value is. You have min, that will find the minimum value in there. You also have the ability to find a mean, which is the average value, the median, which is the actual element that is in the middle in value wise or size of all the other elements in that array, and sum of elements, product of elements, and so forth. There's even a row vector and so forth that you can get, and so a product of elements, sum of elements. There's all these functions in here that are very useful from data analysis standpoint. And I think to highlight this point, I'm going to do a classic example of looking at creating a random die roll and looking at the statistics that come out from that. In order to do that, we're going to have and create a variable that calls our random number. We're going to want to create a random roll from a die. So how can we do that? Well, you've already seen me use a couple of times the rand function. We have two different functions. There are a lot of different random number functions in MATLAB, and I should emphasize, when you talk about computationally in software in any kind of computer, random numbers don't really exist. They're as close as we can get to it. They can be kind of pseudo-random, I would say, but the function that creates it, there's a seed that's generated, and it's meaning that if you click it at a certain time and based on clock of the computer and all these other things, you'll have a specific random number seed that's used to create a random number list. But if you have that seed and you use it in the rand function, you always get the same number. If that's the case, it's not really a random number now, is it? But we use it because it kind of helps illustrate the point. So there are other forms of random number generations within random. The ones that I think are most important are random, which gives you a random value from 0 to 1 that is uniformly distributed. There is no, if you plot it out in the random number function, if you plotted out the values evenly in a histogram, you'd find it be a flat line across it. There's no bias from one to another. The alternatively is the normal distribution, rand n. It'll return a normal distribution of values centered around 0, but it'll be pretty much a bell curve around there in the numbers that come out. So these are different options here. Because a die roll is uniformly distributed, that means that every number on a die, if it's a fair die, should actually be have equal opportunity 1 to 6, right? So if I say clear and that. All right, so now what can we look at? How can we create random numbers? Well, let's play a little bit. I can create a number called roll, a variable called roll. And let's call it die1. Die1. And I want to create it rand. If I say rand and I say 10, that actually doesn't give me 10 random die rolls. That gives me an array of 10 by 10. I don't like that. So let's say I use die roll and 10 comma 1. You'll notice I get a column now of 10 numbers. This is much better. I can play with this. And you'll see here, I'm going to change format back to the format short because it'll be a little bit easier to see. So if I said die1 or CLC, if I say die1, okay, that looks a little bit better. You'll notice theoretically this is all evenly distributed. Well, what I really want now is a number that goes from, that's an integer, 1, 2, 3, 4, 5, 6, evenly distributed. Well, crud. If I try to do this now, what's going to happen? Well, it's only from 0 to 1. So how can I change this number die1 into a value that ranges from 0 to 6? Okay, well, I can multiply by 6. So let's say I say times 6 and hit enter. Well, great. Let's see, and I'll say die1 6. Great. I now have numbers that go from theoretically somewhere from 0 to 6. We don't have anything less than 1, but we have numbers that kind of look like that, but they're not integers. So how can I change that? Well, hopefully, if you know, if I multiply by 6, that means the highest possible value is 6. The lowest possible value is still 0. So if everything's evenly distributed, then if I rounded up to the next highest number, then everything that rolled from 0 to 1 would become 1. Everything that rolled from greater than 1 to 2 would round up to 2, and so forth. We have a nice function on that called ceiling. I think it's called ceiling. Let me see. Help ceil, I think. Yep. Rounds towards plus affinity. That's a nice way of saying it. It just rounds up. I don't know why they don't say that. So we can actually say CLC and say die1. And if I say ceil here of this function, what's going to happen? I get a random die rolls from 1 to 6, I think. All right, that seems reasonable. So, cool. Let's find out how normally distributed this is. If it's even, I should have numbers. If I had a histogram of die 1, now the histogram function should plot out something. I don't know where it is. Here we go. Figure 1. It gives us the numbers of times, something from 0 to 1.5. It's here is 2 to 3. It's kind of giving me these groupings that really don't make sense, but it should be flatlined across. That's not terribly uniform, but theoretically, as we roll more dice, it should become more uniform. So instead of 100, if I said 100, 10, I said 100. I did that, and I said hist die 1 and rolled. You'll see, oh, it's maybe getting a little bit more flat, right? What if I said 1,000 rolls? And then, oops, stop. If I said hist 1,000 rolls, ooh, that's starting to look a lot flatter, right? As long as this is starting to become more and more uniform, that that definition of 1 to 6 becomes valid, right? We should start to see this as an average. In truth, if that's all true, then the average value, the mean of die 1 is around 3.5. So that's not perfect, but still, if all increments come up similarly, it should be 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6. So 3.5 should be the mean value, and we're not too far off from that. So that's good. But now, this is only part of the story we can do. Why don't we take this definition that we just created, and let's go to our editor feature. And now we can actually start to look at things like what happens if we have two random dice and we sum them up. Now you know that in probability the most common die roll is 7, correct? And then the least common, and then as you start to get further and further away from that, from 1 is the least, a roll of 2 is the lowest, and a roll of 12 is the most rare. But you have this nice Gaussian distribution of with 7 being the most common number being rolled on 2 dice and so forth. Can we see that on a function in MATLAB? So if we had die 1, die 2, and rolls, and we're going to take these as 2 column vectors, and we can create a thing called total, where we see what the total value is per roll, and that's going to be equal to die 1 plus die 2. So each position will be summed together, and that will be our total. And we can see, is the sum going to be a histogram? Now I'm going to do this for 1,000 rolls, and we can get this value and see what it is that our results are in this system. So we can say histogram of total, and click and save. and call this die rolls, save, run. Oops, I must have made a mistake somewhere. Let's see what happened. Oh, I see. Someone didn't yell at me. So look here. I have die 1, die 2. This die is not referring to anything. So I can put that there, save, click run, and we get something that's starting to look like a Gaussian distribution, with 7 being the most common number. It's not necessarily perfect, but we are getting something that's getting closer and closer to that die roll idea that we're seeing. So you can start to see the advantages here is just how we can check statistics, how we can check values so rapidly. So you can actually see, if we wanted to know the max value of total, it's 12, which should make sense. We can actually see the minimum value of the total, which is 2, which is very good. And we can start to get, the mean, which die roll. And so this should be close to what a mean of total, and 6.97, very good. That should be the case. The mode of total, 7, because the mode is the value that's in the middle of all the half the numbers are smaller, half the numbers are bigger. That makes sense. Excellent. And so you can start to see that all these things are falling into place, and you can improve this by, instead of going from 1,000 numbers to 10,000 numbers, I can go to 100,000 numbers. And save. And I'm going to open up this figure and close it just so we can see it. Run. And now we have something that's distributing much, much more commonly. Now this is just an artifact of the way this is automatically selecting these bins. If we were to play with histogram a little bit more, you'd see that this kind of falls in place a little bit better. But you can get a sense, again, that this is exactly how we can start to see the distribution and the results that we're seeing in the die roll. And later on, there are ways we could even actually go through and just in a couple of lines find how many times the number 2 came up, find how many times the number 3 came up, and get those totals, and then start to do statistics on, are they occurring in the probability ratio that you'd expect. If we normalize this, will we see those values? And so these are all things that are possible in MATLAB. And again, we did this rather complex and involved calculations in 4 lines of code. And this is, again, where MATLAB really shines, is this ability to find this information fairly simply and very easy to get together. So with that, I will end this conversation and go to the next section. Thank you.